So for the most part, the actual use of the derivative rules for multivariable calculus is the thing that requires some practice. And all that really is being required here is that you sort of build up the ability to you pay attention when there's two variables in a problem, there's two letters in a problem, to pay attention to which one should be counted as the variable and which one should be just treated like a number. And it takes a little bit of concentration, a little bit of practice to do it. But the good news is that the rules are not any different. And in fact, in a lot of cases, they're easier. So for example, here I have an expression with x's and y's, and I'm asked for the derivative with respect to x. So that means I'm going to treat x as my variable. And so for me, that means I'm going to rewrite this because I want this to look like a number times the power of x, x because x is the variable. I want the next term to also look like a number times the power of x, so I'm going to rewrite it as 4y times x squared. So now it looks like something I'm treating as a number times the power of x. And then the last term, 7y cubed, well, it has no x's in it, so it's easy enough to treat that as a number. So that's just rewrite. That's not actually doing a derivative rule. Right? So we've said rewrite before a lot, and that's all we're doing here. But this will help me focus on what's the number and what's the variable. So my derivative, number times the power of x. Leave the number alone. Derivative of x cubed is 3x squared. Number times the power of x. 4y is treated as a number. The power of x here is x squared. So the derivative of x squared is 2x. And then finally plus the derivative of this guy. Well, this guy has no x's in it at all. Plus, so the derivative of something with no x's is just 0. And so I can simplify this as 12x squared plus 4 times 2 is 8. And I could write 8yx or 8xy, either one. But that's my derivative with respect to x. One of the things that you have to get used to is the fact that all of the rules we learned before are still legitimate. So, so in particular, the chain rule. Here we have a bunch of stuff to the third power. And so in our book, they introduce extra letters to talk about this, but the way I always think about it, or have thought about it in this course, is what they're asking here. I have an expression that looks like a bunch of stuff to the third power. And the stuff just happens to be 5 plus 2xy squared. But we know from experience that, that when we're doing a derivative like this, all that matters is that we know that it's something to the third power. The derivative rule for something to the third power is 3 times the same stuff squared, and then times, and I should include another step here. So hang on to that for a second. What I'm really doing is 3 times a bunch of stuff squared times the derivative of the stuff. And we don't tend in this chapter to use this symbol very much, the prime, because that's not very specific. It doesn't tell us what the variable should be. But if we can keep it in our head, remembering what the variable should be, then it's just as meaningful to do that. The derivative there, the prime there, means with respect to x in this case. So what I need to know to finish this problem is what is the derivative of this stuff, 2xy squared, when by the derivative here I mean the derivative with respect to x. And so I might do a rewrite here. I might say I want the derivative with respect to x of, and again I like this to look like something times the power of x. And I don't care what's in there. It can have the other letters or whatever, but I want to see the power of x by itself. So number times the power of x. The derivative of that, well, the derivative of 5 is 0, and the derivative of something times x, some number times x, is just that number. Right? Just like if we had the derivative of 5x, we would get 5. Whatever number is sitting there, that's the derivative of the number times x. So that's where this 2y squared comes from. That's the derivative of the stuff with respect to x. And of course, we can also ask the same question with respect to y, and the expression will look exactly the same. See, my exponent fell here. This is supposed to be a power of 2. But now the chain rule, again, is 3 times the stuff squared. But now when I say the derivative of the stuff, the derivative here means with respect to y. So I just need to know what is the derivative of this junk with respect to y. And this already is written as a number times the power of y. So the derivative of that with respect to y, well, the derivative of 5 is 0 again. And then I have the number, the 2x that I'm treating as a number, times the derivative of y squared is 2y. So 2x times 2y is where this 4xy is coming from. It's also not crazy that we might need to use the product rule or the quotient rule. Here we have the derivative with respect to x, so we're looking for the x being our variable, but you see we have a quotient here where there's some x's in the numerator and x's in the denominator. So I know I'm going to need the quotient rule to do this. So my derivative, just like always, I don't actually try to do my derivative, I just try to write down what it says. It says, quotient rule says my derivative should be the denominator times the derivative of the numerator. So I could use the prime notation and just remember which variable it is, but I'll write explicitly here that I want the derivative with respect to x of 4xy minus 4xy times the derivative of 1 plus x squared y squared. And the denominator is still the same as it is always with the quotient rule. So to finish the problem, the quotient rule is not hard to write down. I just write down what I'm going to do. And all I have to do is make sure that at no point do I change my mind about what the variable is. I've got to be consistent to the whole thing. At all times, the x is going to be my variable and the y is going to be treated as a constant. So I have the 1 plus x squared y squared. The derivative of 4xy, well, I would think of that as this. I would think of as having 4y times x, because I think of number times power of x. The derivative of that should just be 4y. And then similarly, when I have this guy, I want to think of that x squared y squared really as number times x squared. So really it's y squared times x squared. So the derivative of y squared times x squared is y squared times 2x. And that could be rewritten, of course. But one reason I'm not really trying to simplify this as I go is because I know in my heart that all they want to know is what happens when I put 2, -1 in there. And so it's kind of a waste of time to simplify algebraically and then plug a number in. It's much easier just to put the number in to all these different pieces. So for example, if I put in x equals 2, y equals 1, I'll have 1 plus 4 times 1. So that's 5. Four times y is -4. 4xy is -8. Y squared is 1, and 2x is 4. So 4. And that's all divided by this denominator. Well, the denominator is 1 plus x squared y squared. We already did that. That was 5. 5 squared. So 25. So that's the number. And that's much easier just to do each of those pieces and put that in my calculator than it is to do a bunch of algebra here and then just plug a number in at the end. You should get the same thing.